Good morning, everyone. Let's get started. Last week, we looked at Gaussian integrals. We're going to continue that discussion today a little longer to calculate endpoint functions or moments for many variable Gaussian integrals. Just to remind you, last week we looked at the following integral. And various variations thereof of this particular integral, this Gaussian integral. This is the integral that tells us about the moments. There's an A in here as compared to last week. It tells us about the moments of the Gaussian probability distribution. Now, the relevance of this integral will become clear as we transition to path integrals, Gaussian path integrals. Before I do that, what I want to do is spend some time working out the many variable version of this integral here. So before I do that, I'll just record the result we obtained last week up to a factor of 2. Oh yeah. There's one more 2 here, and we're correct. So that's the integral we calculated last week, or almost calculated. Part of it was an exercise. And where we left off last week was in evaluating many variable Gaussian integrals. So there was an exercise which you all did, namely to calculate this integral here. And you all managed to prove, I'm convinced, that this integral here has a very beautiful expression in terms of the determinant of the matrix A and a quadratic form involving J. So the answer is the following to this integral here. And there's an inverse. Crucially, there's an inverse on the A. So this is the generating function for the many variable Gaussian probability distribution. And before we move on to correlation functions and path integrals, I want to spend some time explaining why this is a useful thing. So just by analogy here, if you recall how we could prove this equality here, one way we found to evaluate this integral was to add a source term to the exponent, throw that out, carry out that integral by completing the square, and then noticing that these moments here you could get from this generating function by differentiation. So this is the key trick here, the one that allows us to really get ahead on calculating stuff about Gaussian integrals. This is why we love them so much. Moments of this integral will turn out in a minute to be just equivalent to derivatives of this closed form expression here. So you don't have to do complicated integrals to evaluate the many point moments of this Gaussian distribution. You just need to know how to differentiate, and that's a much easier task. So I'll describe that process now. So we'll look at in some detail the 2-point function of the many variable Gaussian distribution. The object we care about is this one here. What's the expectation value of the random variable xj and the random variable xk multiplied together? This is something that appears over and over throughout classical physics, statistical physics, and quantum field theory. We're going to always encounter these 2-point correlation functions These are the most fundamental building blocks, as we'll see, for all of perturbative quantum field theory. So the way we do it, well, I can already explain how it's going to work, and then I just write out the answer. If we look at this expression here, we see that the seed of this xj, xk is already present in the exponent. So if I differentiate with respect to the right capital J variables, I'll bring down an xj and I can bring down an xk. So on the left-hand side, I know what to do to put an xj and an xk in there. And on the right-hand side, well, it's even better, right? We definitely know what to do here. So having told you how to do it, I'm just going to write out the answer because it's a good little exercise to verify this, but it's not at all challenging. So we want to know the expectation value of xj, xk, but this is not a normalized probability distribution, so we've got to normalize it. Wait on, why did I write j's there? They should be x's. This is not a normalized probability distribution, we better normalize it. And we get an extremely beautiful answer at the end, namely A inverse, but not just A inverse, the jkth entry of the matrix A inverse. Okay, maybe I'll say one or two words to this calculation. Namely, I'll express the top integral as a derivative and then we'll stop. So this is how we can do that integral. This is I should point out, for j is not equal to k. When j is equal to k, it's a slightly different answer. So we look at this generating function over here, and we realize by differentiating with respect to capital J little j and capital J little k, we can bring down an x and a j, xk, xj and an xk. And the normalization doesn't matter. And we evaluate all of this at capital J equals 0. And that's how we actually we can write this two-point function in terms of something that we know how to calculate. The next step is to just substitute that in, do the differentiation. Sorry. Should be a bracket there. We shouldn't evaluate the integral to j is 0 before we differentiate. That would be 0. So we substitute in this nice formula here into here. We pull down an A inverse. That's where we get this A inverse from. And then we're done. So that's how you calculate two-point functions for Gaussian probability distributions. Super easy, very beautiful answer. Very interesting answer. It's the inverse of the matrix A, not the matrix A. This turns out to, as today's lecture goes on, you'll start to get a sense of why we see, of how to connect that result up with things you know from last semester. But the best is yet to come. Okay, this is all very nice, but it's only a 2-point function, and we're definitely going to want more than 2-point functions when we start doing perturbative quantum field theory, or when we ask any more complicated question than what we have on the board. So the question is, how do we evaluate higher order moments for the Gaussian distribution? And well, you know the answer already because you've seen what happens in the single variable case. To evaluate higher moments, we just do more derivatives. And there's a nice little pattern that emerges when you study these higher moments, and we're going to first write out the objects, and then I'll write out the answer. So higher moments, let's look at these guys. Suppose we have an L-point function. We want to evaluate this. Just to remind you, the L-point function is this thing here. All over a normalization. And this is presumably not so tricky, right? You saw how we solved the problem for the 2-point function. We just got to do some more derivatives. That's the answer, right? Indeed it is. But in the many point case, the answer is a bit more intricate because you've got to do multiple derivatives of this function here, so it's inevitable that there's going to be some complications. I'm going to write out the answer, and we're actually going to give this answer a name so you can start mentally connecting this with the stuff we covered last semester. The answer is given in terms of something called Wick's theorem. So this is actually the same Wick's theorem as last semester, but the proof is a whole lot simpler. And the connection, the objects at play are a whole lot easier to describe. You don't have to describe normal ordering or time ordering. All of this comes as a consequence of this kind of more abstract version of Wick's theorem. So the answer is the following. So I'll just write out the answer, and I'll leave it to you to verify. Again, I think proof by induction would more or less do the trick. So we know that we're going to bring down lots of factors of the inverse of A. That's true. We definitely bring those down. Yeah. This is for the case that L is even. When L is odd, we get a different answer. And the L is odd case, you already know just by thinking about symmetry arguments, it's 0. So you don't have to do any calculation there. So you don't have to worry about the L is even case. Oops, a J there. What we get is a sum of products of matrix elements of the inverse matrix A. Wick sum. So this expression here it's hard to overstate how important this expression is here, because what we've taken is this complicated nonlinear L-point function here, and we've managed to express it in terms of the products of these objects here, but these objects have another name. We already identified what they were. These matrix elements are none other than two-point functions. So we've managed to derive an expression for an L-point function in terms of a product of two-point functions. So physically, a question?
So the question, wouldn't the application of Wick's theorem lead to another expression for the two-point function? Wouldn't we get A inverse jk plus A inverse kj?
Right. That's true, but A is symmetric.
Okay.
So the inverse is also symmetric. So there's a proportionality factor here that I haven't written. I'll put, for the moment, we'll put proportional too. We'll sort that out in a second. Yeah, A is symmetric, so AKJ equals JK. What we found is that we can express this L-point function here in terms of two-point functions. So physically, this is extraordinary, right? We're saying that if these were the correlation functions for a physical system, once you have determined the two-point functions by experiment or whatever, then you actually know all the higher order functions, all the higher order moments. They're all just functions of these two-point functions here. That's why we love Gaussians so much, because we know all the observable data about them once we know the two-point functions. Now I'll do an example to illustrate this theorem. Let's work out a four-point function. And once we've done that, we've more or less going to see. We're never really going to go beyond four-point functions in this course. Maybe a little bit beyond. So you have all permutations on four labels that you have to worry about. All the way down to, so you have to worry about all 24 permutations on four letters to begin with. There's 24 permutations, but how many of them lead to the same answer? Well, any time, as we've observed just before, any time you have pi 1 is 2 and a pi inverse 2 is 1, well, you can get the same answer as if you had 1 or 2. So you've got to divide by this overcounting to find the number of unique terms that you have to worry about. There's actually only 24 divided by 8 unique terms. Work out these unique terms, see what they look like. We have 3 to worry about. 24 divided by 8 is 3. And here they are. There's the 3 unique terms that can come after you exploit the symmetry of the matrix A. But because we have another word for A inverse, it's A, J1, J3, in this case there. So we have this very beautiful expression for the 4-point function in terms of just 2-point functions. There it is there. And we have a little graphical mnemonic to help us remember these terms. It's very tempting when you see 4 things collected in pairs to draw lines between dots. So we're going to associate a diagram to each of these terms here. So this term here, we have 4 dots. We label them by J1, J2, J3, and J4. And every time we have a 2-point correlation function involving variables JL and JM, we draw a line between the corresponding dots. So that's the picture we associate with this term here. That times that is this picture here, plus. This picture should start to look familiar to you. So we have the following graphical representation for all the terms in the 4-point function. It's 3 unique diagrams here. Not bad. These are exactly Feynman diagrams. This isn't an artificial diagram that I've written here. this is exactly going to turn out to be a Feynman diagram when we substitute a very particular matrix for the matrix A. And I'm going to tell you in a moment. I just want to, well, firstly, mention that proportionality result there. We sum over unique terms up there, and there is no proportionality constant. So that's the answer. You know how to work out the unique terms. You draw pictures as what is the most efficient way. So let's just look at the case L is 6. So the number of terms that we get here will be the number of pairings of points, of 6 points. And we can work that out because the first pair, how many do you have to select from? Well, you have 6, choose 2 possible pairs to select from. And then you draw your first pairing. And then you want to select another pair. So how many pairs are left? Well, that's 4, choose 2. So you've got to choose, you've got to connect this one or that one. And then you've only got 2, choose 2 possibilities left. So the number of terms you have to worry about is just the number of ways of pairing up two n points, or an even number of points. I'll just draw a couple more terms. There's another one. You can see where this is going. It's a bit tedious, just like Feynman diagrams do, but there is a straight out recursive algorithm for writing out all the possible terms. Plus dot, dot, dot. I'm not going to go through this. And the value we associate with that diagram, of course, is A inverse. For each pair, we've got to associate an inverse matrix A. Oop, there's another pair. We've got to associate an inverse matrix A. That's 3, what do I call this? 6. And then one more. 4, 5. Plus dot, 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 dot. And that's the actual statement of Wick's theorem. You take the even number of points, draw them in the plane, draw all possible pairings, then associate with each diagram this value like that. I leave the proof as an exercise. It's an exercise in differentiation and induction. It's actually, this proof is available all over the web because it's of relevance from everything from statistics through to quantum field theory. So what I want to stress here is two features about this discussion so far. So feature number one, which is hard to understate, is that we can calculate all the moments for the Gaussian distribution. I mean, wow. You don't often get given a gift like this, that you've got a probability distribution and you know everything you can measure. And the second very beautiful and relevant feature for us is that we have this diagrammatic calculus for how to calculate these L-point correlation functions. We draw these pictures down very suggestively like Feynman diagrams, and they will in fact turn out to be Feynman diagrams. So the connection between Feynman diagrams and the whole quantum field theory perturbation calculus from last semester and just Gaussian integrals that you met already in high school is in fact a direct connection. It's just we have to fill in some important information. What's this matrix A in the case of perturbative quantum field theory? So I'm going to discuss that now for a couple of minutes in the terms of an example. And then I want to get on to what do these correlation, to really arguing that these correlation functions have something to do with Feynman diagrams. I mean, after been through a canonical quantization course on quantum field theory, and after working through the infrastructure you need to set up just a two-point correlation function, doing things with Gaussian integrals is awfully attractive, right? Because the number of moving pieces you have to remember is very small. You have to remember how to do Gaussian integrals. You have to remember how to do a generating function. And you need to remember two more things, right? You need to remember the path integral, how to derive that. But the mnemonic for that is also very easy, right? You just put in the completeness relation. And you need one more thing. And then you can remember how to derive all of relativistic quantum field theory from scratch, essentially. So that's why I think it's extremely attractive, this path integral formalism, for remembering the details. All right, let's answer the question. What is A in the context of a path integral? Well, remember, we have this expression for the propagator. So we'll do it for non-relativistic quantum mechanics. Because as we saw, a relativistic quantum field is nothing but a non-relativistic set of non-relativistic quantum systems with particular properties. So let the potential V for our source classical system, let it be a quadratic function of the canonical variables. Then we had this expression for the propagator for our system. And so you can immediately see how this is connected to the Gaussian integrals we've just done, right? The minute we work out what that A is, we've already worked out our Gaussian integral for the Gaussian path integral. All right, what's A? This is the big question. Well, it's easy to work out what Q transpose QA is, because we know what should be in the exponent. Oops. So that's what A, for a typical system of a chain, oh yeah, I didn't tell you what the Hamiltonian was. So we imagine we have a chain of classical harmonic oscillators. This is the typical kind of expression you would encounter in discretizing a relativistic quantum field. But I mean, there's another way of writing this, right? It's just kinetic energy plus potential energy of our classical system. And we haven't quite yet determined what A is. We have this expression here. It's obviously quadratic in terms of Q's, but what's A? You know, the left-hand side is quadratic, the right-hand side is quadratic. So for this example here, we'll just go through this term here and explain how that can be captured by a matrix A. So the kinds of matrices A that we're going to encounter have a very particular form. They look like a tridiagonal matrix. This is in one, let's keep this in one spatial dimension. Just for simplicity, it's a nice little exercise to do this for every system that you consider. So A, what does it look like as a matrix? Well, we've got to get qk times qk plus 1 times m divided by epsilon with a minus sign. So the way you can get that is m over epsilon, a matrix that looks like this with minuses. So you can go ahead and check that when you substitute for Q transpose and Q here, with this matrix there, you get exactly this answer. Of course, there's diagonal terms. So there's twos here. And on the diagonal, oh no, there's no twos. Sorry. On the diagonal, there are, however, twos. So here we get qk plus 1 squared, but we also get, in the previous term in this sum, qk plus 1 squared, so we get it twice. And we get m over epsilon. We get 2m over epsilon in diagonal entries. And the rest is 0. And plus there's some potential energy matrix that we haven't yet worked out. So you can go ahead and work out, just substitute in for Q transpose in Q, and confirm that what the quadratic expression in terms of Q you get from this equals this first term here. I haven't yet touched this term here. But whatever that term is, it's going to be a quadratic function of Q's. So there's going to be some other matrix that corresponds to it. I won't write it out. Just this first term here is sufficient to explain what the kinds of matrices A look like in these expressions up here. And we can just straight out evaluate now this path integral for any quadratic system, because we know the answer. We know how to do a Gaussian integral over k variables. We even did that last lecture. And we get a very simple answer. We get some infinite constant times by the inverse square root of the determinant. So you just look up the Gaussian integral. And this is a remarkable result. It also should cause you some slight concern. This infinite constant here is a bit worrying. But there is some beautiful features to it. Now, I claim the constant here is not going to be a worry for you because we never actually measure. This is not an operationally well-defined quantity here. The things that are operationally well-defined are L-point functions. And if you remember, L-point functions are defined to be the moments of integrals like this divided by that normalization. And that normalization is exactly that infinite constant again, and it wipes it out. So it actually becomes a finite number after you normalize things. So I'll sketch that in the next board, and then we'll get to connecting these correlation functions to actual observable quantities. So if you put in to this path integral here some arguments with these variables q, then it's not particularly difficult to argue that this quantity is finite. Okay, that's straight up just substituting I times A in the place of A in the previous things we've done. The only difference is turn x's to q's and change A to I times A. And you will get a finite answer for this calculation here, as long as A inverse is defined. That's great. We like finite answers, and it's a hint that these quantities might be operationally well defined. But there's no, at this point here, you have every right to be suspicious of this object here. What's its interpretation in terms of the original quantum system that we started with? What I've written down here is a purely classical Gaussian integral here, and I've drawn angle brackets around it and written this down on the left-hand side. What has this to do with our physical quantum system to begin with? So it turns out this will be equal to something that you're very familiar with in quantum field theory. And we'll do that derivation in a second. But before we do that, I can't help but discuss this matrix A a little, just to give you a sense of how to invert it, and that it's actually an easy matrix to invert. it's all very well to express things in terms of inverses of symmetric matrices. If you can't compute the inverse, then you're lost as you were when you began. But it turns out these matrices are very beautiful and we can invert them. And in fact, you've been inverting them for a while now. You're used to doing this. So observation 1 is that A is a tridiagonal matrix. And if we give periodic boundary conditions, then this tridiagonal matrix has a very particular form. Namely, the ajkth entry is really some function of j minus k, of the distance, the difference between j and k. Now, any such matrix, or modulo n, which is the number of sites or oscillators in the chain. So whenever you have a matrix with a property that its jkth entry is just some function of j minus k, then it turns out you can not only invert this matrix, you can diagonalize it and work out its eigenvalues and its eigenvectors. And this is such a useful fact that I can't resist mentioning it now. So we're going to build the following unitary matrix, Q. Q of jk is 1 on root n e to the 2 pi I j k. So we build an n by n matrix whose jk entry is e to the 2 pi I j k divided by root n. And it's amazing that this matrix is in fact unitary. It's a lovely little exercise, that one. And it also has another property which is pretty amazing. Q to the power of 4 is identity. It's not relevant for this lecture, but I can't help but mention it. And notice that Q is diagonal. Oops, no it isn't. That is. So you can diagonalize A, and once you can diagonalize A, you know how to compute its inverse, because you can work out its eigenvalues and its eigenvectors. Well, Q is nothing other than a discrete Fourier transform. Now, if you like, this is the reason why Fourier transforms pop up everywhere in quantum field theory and in physics. When you discretize the system and you want to solve it, you notice it has a symmetry, you exploit that symmetry, and you can often spend enough symmetry to simplify the system down to something you can calculate. And once you know the eigenvalues, you definitely know the determinant as well. This is something that will be useful a little later in the course. The determinant's the product of the eigenvalues. This is something that will come in handy quite a lot later on. So this is just a superficial overview of how we get from Gaussian integrals to quantum systems with quadratic potentials, or vice versa. We're not quite done yet, because we haven't yet given an interpretation for this L-point correlation function here. It's a nice thing to write down, it's finite, but beware, it's easy to write down nice things that are finite in quantum mechanics that have no operational meaning whatsoever. So I have to convince you that not only is that thing finite, but that it's useful. Because it relates to something that you need. So indeed it does. So these L-point functions here relate to something really familiar to you, but to express that best, I'm going to start doing path integrals in terms of fields, and you always have to remember that when you want to make sense of it, you have to discretize, evaluate, take continuum limit. So as long as you remember that algorithm, then you'll be able to make sense of things that I'm about to write. All right, so this is the first challenge. Here's a path integral expression. Now, this doesn't make sense as written. To make sense of this, you have to follow the prescription of discretize, evaluate, continuous limit. Always, when you see an expression like that, you should be thinking, how do I discretize, evaluate, and take a continuous limit? So discretize, I'll do that first step, and then the rest is yours. Right? You define a grid on space-time, or on just space, and the field evaluated at grid location xj is just some canonical position variable qj, and then this immediately discretizes into an integral just like the one up above. So we did those steps in the previous lecture. And then evaluate was self-evident, and taking the continuous limit will also turn out to be pretty straightforward. So in this point in the course, the demands on you get higher until you're used to path integrals. So at some point, you will be able to do mentally these steps pretty quickly. I'll write down an expression like this. You'll have some practice at discretizing, evaluating, and taking the continuous limit. And then you'll say, okay, I can imagine what this integral looks like in terms of q's, and I can make sense of this expression. And that's what we're going to do from now on. I'm not going to every time discretize, evaluate, and take the continuous limit. That's always your job. Our job is to reason about this object here. So consider this object here. So this is actually a two-point function. Some kind of two-point function. However, I haven't taken the normalization out yet, so you've got to be a bit careful about normalization. Now we have some boundary conditions. So we assume that at time minus t, our scalar field has to be equal to some initial field configuration phi a of x. Remember, this is all classical. All this data from here on in is classical. And our field at time t at position x is just some other fixed boundary field configuration like that. So what's this got to do with anything quantum? I mean, this is a classical expression. What's it got to do with anything quantum? Well, This is really a very beautiful explanation. I really like this one a lot. First step is to turn this path integral measure here. Remember, it doesn't make sense. You have to discretize it first. We're going to point out something kind of obvious. So that's the same as integrating over a field configuration phi 1 at some space x, some field configuration phi 2, and integrating over the full field. But we demand that at a certain time, namely the time x1 naught, the field in this measure here is equal to that. So it's actually easier to write it out than it is to explain it. Oh, sorry, these are spatial fields at a fixed time slice. Okay, this is like saying I integrate over all functions. That's the same as integrating over all functions that at 2 points are fixed, and then integrating over all those the values of those 2 points. I'll draw a picture. So you have some, imagine integrating over all functions. This is d phi, all functions. But now imagine fixing this point and this point to be a specific value. Like, I don't know, f1, f2. Then integrating over all functions is like integrating over all functions which take the value f1 at point x1 and the value f2 at point x2, and then integrating over all f1 and x2. And why not just call it phi? Like that. That's all that's saying. That's a little picture to help you remember that measure. Right, things can only get better. So we have this very neat but identification of the measure here. And then we're going to write our 2-point function now. 2-point like function. It's not quite a 2-point function. Using this simple observation there. So this is d phi 1, d phi 2, d phi with boundary conditions. And then, well, you know, we did it for a reason. That's because phi x1 was there and phi x2 was there. And we're going to see how useful this is in a second. Because I'm going to undo the derivation of the path integral a little bit and substitute for this integral up here. So I think I'll use the whole board for this. Okay, a little puzzle for you to work out why this is the same thing, but it's not a difficult puzzle. You just substitute what you know about path integrals. And you will see that when you do the path integral from phi 2 to phi b, and you do the path integral from phi 2 to phi 1, and you do the third path integral, that it's actually equal to this path integral up there. Pretty cool fact. All right, that's what you get. Proof by substitution. You just substitute in the path integral here, the one in here, the expressions you have for these things, and you will see it's really the same as that. Now, so note, in the Schrödinger picture, if you apply a field operator to one of these field configurations, you get phi 1 of x1. So yeah, a classical field configuration is an eigenstate of the field operator in the Schrödinger picture. This is an intriguing observation. How is this useful? Well, what we're going to do is we're going to exploit this to undo this equation and put field operators in here and over there. Fabulous. Oh, it's also worth noting that we have a completeness relation. So let's insert in place of these phi's original field operators, and we get, oops, what do we get? All right, I'll write out the intermediate step. I apologize, there's one problem with what I wrote here. And the problem is I actually already evaluated that path integral. That's not there.
Sorry.
Yeah?
Is there any difference in presentation that you use phi of x1 or phi 1 of x?
There is, oh yeah, you can see phi 1 of x is a state. Sorry, phi 1 ket is some kind of state.
No, I mean in the line above, yeah.
Oh, did I write phi 1 of x?
Yeah. Then you use
Oh, I see. Yeah, okay. We sort of do this semi-commonly. Yeah, that's an unfortunate notation. You're right. So when you see phi 1 of x1, that really means phi of x1. Yeah. Sorry about that. That's a bit stupid. All right, so the whole point of this line was that we did one of the path integrals. So this was, so let's do that path integral. Now we have this nice quantum expression here. And then exploit this information here to write that nice quantum expression as something even more suggestive. Oops, that's a 2, of course. Mm-hmm. And then we're going to use the completeness relation. This is the best bit here. So we get rid of all the classical stuff, and now we have only quantum stuff left behind. So that goes away thanks to this. And so at the end of this expression, we're going to end up with something. And this is all, I should say, for the case that x2 naught is greater than x1 naught. If x2 naught is smaller than x1 naught, we get a different expression. Yep.
Did you use the Ket-Bras V2 twice?
Did I use the Ket-Bras V2 twice? Oh, I did too, didn't I?
But now the great arrows are wrong, I think. So you connected the integral over phi 2 with the phi 1 bracket Ket-Bras.
The integral of, oh gosh, yeah, I did too, didn't I? Ay, ay, ay. Okay, so I connected the integral. Oops. Okay, so this is a purely quantum expression here, but we have a name for that thing, up to a phase factor. So, what is this thing? Well, it has a nice name. The time-ordered expectation value of the operators in the Heisenberg picture I believe there's a minus sign there. So that's something we've seen before. So we've got something that looks awfully similar to an object of central importance in quantum field theory. So the expectation value of the time-order product as some field operators. We have these annoying factors here, there, but those annoying factors actually play a crucial role they become the S matrix that you need in defining the endpoint correlation function for a quantum field. So take the limit t is infinity, and we end up with the following expression. And this is the central expression that connects classical path integral technology with quantum observables. This is the important one. The interacting vacuum time-ordered product of quantum field operators at x1 and x2. We need a yeah, it's the interacting vacuum. This is the one we care about. That's equal to the limit of this ratio of path integrals. There's a couple, I mean, there's some small steps to evaluate there. Yep, question?
Sure about the minuses in the exponentials in the first expression?
I'm pretty sure about the minuses and the exponentials. Okay. Because in converting from Schrödinger to Heisenberg picture, so we have a field operator in here. We end up with, well, it does indeed look like a plus sign, doesn't it? No, actually, I'm not sure about that minus sign at all. I make it to be a plus sign. Yeah. No, actually, there was an error. I can see the problem. Yeah, it had to be a plus here. So you have to evolve in time. Yeah, there was a plus sign in there. I apologize. So there was a plus sign here. Okay, you have to note that. And there, it really is a minus sign up there. Oops. Yeah. Okay. So we are done for today. We've derived probably the most important formula for the whole course. We've shown how to connect this path integral, this essentially classical object which sums over classical data and multiplies by a phase. We've shown how to connect this classical object here to this quantum data here. This is the observable stuff that we can really probe in experiments. Furthermore, we've achieved a double triumph, because when L is quadratic, we know how to evaluate this object here. You first discretize, then you end up with a Gaussian integral, which you can just do by using the formulae we derived, substitute the answers in, and then take the continuum limit. We'll do that next lecture, and we'll see that the answer here is equal to what it better should be, which is the inverse, which is the propagator, the Feynman propagator, which is the inverse, if you like, of the Klein-Gordon operator. So A is the Klein-Gordon operator for scalar quantum field theory. There is a many particle version of this for L operators. I think you can work out how to derive it. And it's on this basis that we will be building the rest of this course. In the next lecture, as I said, we'll talk about scalar fields just briefly. How do you do them in this path integral language? Then we'll move straight on to fermions. How do we do all of this story when we have fermions, which are anti-commuting operators? What on earth do we put on the right-hand side here? And that will keep us occupied for a good number of weeks. But at the moment, I think we will stop here. Thank you very much.